Welcome to the end of chapter 3. So we had 4 sections in chapter 3 about radian, measure, and the unit circle. And in this 4th and final section, we only have a couple of things to look at. So if you can see happily, only got 11 slides here, and we want to look at linear speed and angular speed. Those are the 2 concepts for 3.4. So here's the first one. So linear speed, just for me to give the concept, and then we can look at the details and the definition on this slide. Imagine that the circle is a track that you can run around or drive around, a car track or a track and field track. So your linear speed would just be how fast you're going around the track, how fast you're literally traveling along that pathway. So they're describing that by saying, suppose a point moves at a constant speed along a circle of radius r and center O, and they've got this nice picture here. So the linear speed is how fast the point is moving. So you can imagine the point is a car driving around in a circle or a person running around a track in a circle, and it's literally just how fast they're going. And as usual, speed is a measurement of distance divided by time. And they're using a v here to represent it. It says if v represents the linear speed, and that's because v stands for velocity. So I don't know why they wouldn't at least show you that word, but so v is the velocity or the speed of the point traveling around a circle or something like that. And so the distance traveled would be how far along the circle you had gone. And as we've been seeing recently, that's called arc length. So if I look at the distance traveled by the point P as it left the starting point B and went up to where it is now, that's the distance along that part of the circle. Well, that's the arc length for theta there. In fact, if that's a unit circle, then that would actually be the measurement theta in radians. But if it's a bigger circle, if it has a radius r, then you have to multiply theta by r to get that arc length. So I'll put that as a reminder that the distance traveled around the circle will be r times theta as a reminder. So that's how far the car has driven or the person has run around the track. And you divide that by the amount of time it took them to do that, and that's how you get this linear speed. Linear speed is the thing. Call this. And here's our little formula here. Linear speed. So arc length divided by time, basically. So if, for example, we knew that the arc length was 2 feet and that the person or the point on the circle had been traveling for, we could say the time was in seconds, like maybe 7 seconds, then I would go, the velocity was 2 feet divided by 7 seconds, or 2/7 of a foot per second as a rate of speed. So because you're dividing a length by a time, you're usually going to get a unit of length like feet, miles, something like that, divided by a unit of time like seconds, minutes, hours. Obviously, one of the more common speed unit measurements that we're used to, at least in America, is like miles per hour. Miles being the measurement of how far you've gone, hours being the measure of how much time it took you to go that far. But you might have feet per second or kilometers per hour or other types of measurements of distance and time. But you just make this fraction, and then that gives you your velocity or your speed, and that's, in this case, the linear speed. Okay, so the next thing is the second concept, and we're just going to introduce them together, compare them, and then we'll look at a couple problems that utilize these concepts. So then the other possibility is to consider angular speed. So linear speed is literally how fast you're moving around the circle if you're riding along the circle. Angular speed, you can imagine by you sitting in the middle of the circle, watching the car or the person go around the circle. And as you turn and follow them, you are creating an angle, an increasing angle that grows bigger and bigger as you turn and rotate. So your position of rotation in the middle of the circle sweeps out an angle, and that angle grows and changes over time. That's the angular speed. So as point P moves along the circle, ray O to P rotates about the origin as it follows along with the point, as if you were looking at the point. That would form that ray as you're looking at the point. The measure of how fast angle BOP, the angle from where the point started to where it advanced to, that angle, how fast that angle is changing is its angular speed. So if we're still more comfortable with degrees, you could think about it as like maybe I'm sweeping out an angle of 45 degrees every 10 minutes. That would be kind of slow, 45 degrees every 10 minutes. But of course, quite regularly, we'll expect that degrees won't be used, that instead radians will now be used. And if you're doing radians, then you can talk about how many radians per minute or per hour or per second of rotational angle is being changed. And so the symbol that they use for angular speed is this funky looking W. It's actually called an omega. It's a Greek version of a W kind of. But you could think of it as this little funny W. Remember theta, the angular measurement, that's a Greek letter too. So these are always these Greek letters showing up. But again, you just make a fraction. In this case, you measure what angle was changed over the period of time in theta, and then you divide that by t. So it states here, W is the angular speed, theta is the measure of the angle, and it says specifically here in radians. So you can think of it initially in degrees, but you're pretty much always going to be asked to do your calculations in radians when we're doing this kind of a thing. So let's look at an example. Let's say that you opened up a theta of pi over 2. And pi over 2 happened in 7 minutes. And pi over 2 is in radians. Well, we can think of pi over 2 still quickly as 90 degrees. So you did 90 degrees in 7 minutes. But if I want to calculate this W value using radians and the time given, then I would do pi over 2 radians divided by 7 minutes. Now I could type that on a calculator and take pi over 2, see what decimal that is, and then divide by 7. And that would give me a decimal version of how many radians per minute. But I can also simplify this fraction a little bit by dividing the 7 and having it join the 2. And I would get pi over 14 radians per minute. And that's the exact value. And again, you could also simplify that or convert that to a decimal on a calculator if requested to do so. But if they asked for the exact value, you would say pi over 14 radians per minute. And again, that's how many radians of angle that you're increasing every minute. Questions, comments, discussions about that? All right, so those are our two concepts for 3.4. The thing now is to compare them a little bit, to think about them, and to see how they might show up, or they might ask you to calculate some of these in a problem of some type. So they do a nice little summary here. So angular speed W is theta divided by t. W is in radians per unit of time, minutes, seconds, whatever. Radians per unit of time. And then linear speed, that's how fast the point is actually traveling around the circle, is arc length divided by time. And they point out, as I did on the earlier slide, that if you have a radius that's not 1, if you have a bigger radius circle or something different, then the arc length is just that radial measurement times the angle in radians. And so that means you could convert this formula from S over T to R times theta over T. And if you do that, you can also take note that theta over T is W. And so if they replace that or substitute theta over T with W, then you get another way you can think of the speed of the point, or the linear speed, is it's the radius times the angular speed. So this equation here says linear speed is radius times angular speed. So how does all of this become helpful? Well, when we start thinking about doing problems. So let's take a look. Yeah, this looks fun. Woohoo. Suppose that point P is on a circle with radius 10 centimeters, and ray OP is rotating with an angular speed of pi over 18 radians per second. Angular speed, so that means this is W. And radius of 10, I'm just going to write up here, this is R, because then if we want to find what's going on or relate to these formulas, we can use those same letters from these formulas. So the first thing it says is to find the angle generated by P in 6 seconds. So you can sometimes draw a picture to try to visualize these. I think that helps most people in most cases. And so we know that the radius is 10, just to sort of put that in our mind. And that we know there's this ray that's rotating around. And we're going to say that W is equal to pi over 18. And that's radians per second. So that means every second, you're going to get pi over 18. So if we want to know the total angle generated, the total radians, then they'll do it here. But the idea is that we know that theta over T is given, and we want theta, so we would multiply that by T, and that would leave us with theta. So the way that translates here into this problem is that theta is equal to pi over 18. That's the radians per second. And if I multiply that by 6 seconds, then that'll tell me how many radians that we went through. And if I simplify, 6 goes into 18 3 times, and that would give me pi over 3 is the radian angle that it would be covered after 6 seconds. So they're sort of setting up for that here. Let's see if they just do that. No, they didn't. So that's how you would do that. So they told us W, they told us T, and they wanted theta. And so W was theta over T, and we know what T was, so we multiplied that by T, and that left us with theta. The best way to think of that is the rate. It's like you're driving. If you're driving for 20 miles an hour and you go for 3 hours, you would multiply 20 miles an hour by 3 hours to see you'd gone 60 miles in those 3 hours. This is your speed, just like speed in a car or on a train or speed walking or on a bicycle. If you multiply speed of how quickly you're going by how long you're going at that speed, you get how far you've gone. In this case, this is angular speed. So angular speed times time gives you the amount of angle that you swept out. Linear speed times time will give you how much of the circle arc length you traversed, how far you went around the circle. Maybe that's what they do in B here. Let's take a look. Find the distance traveled by P along the circle in 6 seconds from part A. All right, so as we saw in part A, that you've traveled pi over 3. That's the radial distance that you've traveled. And remember, so now we know that pi over 3 is theta here. And the radius was given to be 10, I think. Yeah, 10 centimeters. So if I multiply that by the radius of 10, then I get 10 pi over 3, and this is in centimeters is the length that they're using here. So in part B, to find the distance traveled, once I know the angle traversed was pi over 3 after 6 seconds. So I multiply that by the radius size to get how far you went around the circle. Lastly, it says to find the linear speed in centimeters per second. And so they've kind of done that for us, so we can look at that. So the linear speed per second is going to be arc length divided by time. And so we just calculated this arc length up here. So they plug that in here for S, and we know the time to do that was 6 seconds, so they plug that in there. And then if you simplify this, you get 5 pi over 9 centimeters per second. Now, we could have gotten that also without doing something quite so fancy, since they gave us the W, which is theta over T. They gave us that that was equal to pi over 18. Well, if we want to convert that from theta over T to S over T, we just multiply by 10. And if you multiply by 10 and reduce that, you get the exact same number. That seems a little bit more straightforward to me than what they did in this little formula, but either way it will work. So we basically have these two little formulas for linear and angular speed, and we're going to sort of use those back and forward different ways. They'll give you a couple of parts and ask you to find another part. So you have to kind of look at the parts they give you and plug those in and find out how to get the part they want. Might be theta, might be linear speed, whatever. All right, so here's one that's a little bit more wordy and not with just a nice picture. And usually when that happens, I do recommend people draw a picture. A belt runs a pulley of radius 6 centimeters at 80 revolutions per minute. So what is all of that? So a pulley is where a belt is somehow attached to a circle and sort of runs around the circle like this. Belt sort of runs around the circle. And so as the belt travels one way or another, it causes the circle to rotate. The circle is the pulley. We know that the circle has a radius of 6 centimeters and that it goes around at 80 revolutions per minute. So here's the tricky thing we have to figure out, 80 revolutions per minute. So first question is, find the angular speed of a pulley in radians per second. The angular speed, how much angle is changing? So what we have to do is go from revolutions, which is sort of a whole circle around the one trip around the circle, to being what that would be in radians. We have 6 seconds. I'm sorry, we don't have 6 seconds. We have the radius is 6 centimeters, but that has nothing to do with the angular change. We just need to know 80 revolutions per minute. So I'm going to point out that 80 revolutions is 80 times 2 pi radians, because one revolution is 2 pi in radians. And so if you did that 80 times, you'd multiply that by 80. And that gives you that you have 160 pi radians. And you're doing that per minute. So if I divide that by minutes, that's the angular speed of the pulley. So they're describing that all here. I just sort of used my words to try to guide us through the process, but they do that here. They say take the 2 pi radians in one revolution, multiply it by 80, and you get 160 pi radians per minute. Now they want this in seconds. So the last step of this would be to go from minutes to seconds. And so as they point out here, there are 60 seconds in 1 minute. So if I go 160 pi in 1 minute, then I have to divide that by 60 to see how much of that you did in 1/60th of a minute. And that ends up reducing down to 8 pi over 3. Let me show you what that looks like in unit analysis for those who've had any thoughts about that. If you have radians per minute, and you want to convert that into radians per second, then the minutes needs to be changed into seconds. So you would multiply that by a measure of units that's minutes in the top and seconds in the bottom, because the minutes then cancel out and then you're left with radians per second. So if I have 160 pi radians per minute, I'm going to multiply that by a fancy 1 that has minutes in the top and seconds in the bottom. Now, how do I make a 1 out of minutes and seconds? Because 1 minute is the same as 60 seconds. So if I multiply 1 minute over 60 seconds, that's the same thing in the top and the bottom. That's a big 1, so it doesn't change the value of my total. But the minutes in units cancels, and I have 160 divided by 60 is radians per second. So that's an alternate way to think about unit analysis to do the same thing that they just did right here. But we just figured out how many radians per second the pulley is rotating based on the belt pulling it around. So let's take a look at part B here. It says find the linear speed of the belt in centimeters per second. Linear speed. So linear speed is r times angular speed, which we just calculated. We know r is 6 centimeters. So they multiply the r value times the w value we just got, and they round off to the nearest whole number, it looks like in this case, and they get about 50 centimeters per second. So that means the belt is traveling 50 centimeters per second at that angular rate for the pulley. And again, this formula came from our table that we had in the very beginning. So if you know W and you know R and they want the linear speed, you just multiply angular speed times radius to get linear speed. And there's one more to take a quick look at to finish up. A satellite traveling in a circular orbit 1,600 kilometers above the surface of Earth takes 2 hours to make an orbit. The Earth is approximately 6,400 kilometers. I think they're saying, yeah, they're drawing it in the picture for us here. The Earth's radius is 6,400 kilometers. Let's change colors. So that's this length here, as they've shown. And how far it is above the Earth adds to the radius an additional 1,600 kilometers, so that's the radius of the orbital circle created by the satellite as it goes around the Earth. So we want to do the 6,400 plus the 1,600, which looks like 8K. So there's an 8,000 kilometer radius of rotation of the satellite. And it takes 2 hours to make an orbit. So that's one rotation, that's 2 pi around. So 2 hours gives 2 pi rotation in radians. All right, so in A it says approximate the linear speed of the satellite in kilometers per hour. So first they find that radial length of 8,000, as I did above, because you need the R. And they point out that for one orbit, that's 2 pi, which is what I described above. So to find the linear speed, we want to go the distance traveled per hour. Distance traveled per hour. So they're saying first we're going to get the distance and then multiply by how many hours it takes to go that. And so the total distance was r times theta, and that gave us 16,000 pi kilometers. The total time is 2 hours, takes 2 hours. So when you make that fraction, you get 8,000 pi, or approximately 25,000 kilometers per hour. And that's the linear speed, but in this case, that's the speed the satellite is traveling around the Earth. So then it says approximate the distance the satellite travels in 4.5 hours. So you'd multiply that speed times 4.5, and they get 110,000 kilometers per hour. And that's it.